Live interaction with an astronomer. Today we have the prestigious Dr. Rintu Nath, and he is here to talk about the wonders of the universe. Before I give an introduction of Dr. Nath, I encourage all students to submit their questions in the Google form pinned to the live chat. Dr. Rintu Nath is a scientist F and the head of the Information and Communication Technology branch of the Department of Science and Technology. He has over 2 decades of experience in conceptualizing, executing, and managing large-scale science and technology programs throughout the country, and has played a key role in transferring technology through academic and industry collaboration. He is a domain expert in distributed computing and is one of the experts members of the National Knowledge Networks, National Supercomputing Mission, and National Language Translation Mission. He has written 60 research papers and articles, as well as edited 22 books, 6 book chapters, and 3 books he has authored. One of his books, A Moment in Mathematics, is internationally acclaimed and translated in Spanish, as well as other Indian languages. Dr. Nath, the floor is yours.
Thank you. Only thing is I'm not able to see my audience.
The audience is actually live on YouTube, so since we are having a very large crowd, it is easier that they are on a different platform.
Okay.
And that way they won't overwhelm the speaker with their questions. So we are currently the best way to say is we are like currently the voice for them. We help them submit their questions to you.
Right. Okay. So I think we should straight away start with my presentation. Let me start my presentation. You need to tell me, is this...
Your screen was visible, sir.
Is visible? Okay.
Yes, it's visible.
Okay. So I have not kept a very specific topic. It's mostly general, and I would like to see how the question comes, and then we can explain it in detail. I've kept a few of those exploring. Yeah, tell me.
Sorry to disturb you, but your screen just disappeared. Could you reshare your screen, please?
Is it?
Yes, the screen is visible now, sir.
Okay. Let me make it a full screen. Is it now visible, full screen?
Yes, sir.
Okay.
No, sir, no.
Oh, I think there is something wrong. The moment I'm going to go for a full screen, it disappears. Okay, I understood. Okay. Let me again share. Okay. I think that's fine now. Yeah. It's okay. Is it visible?
Yes, sir. It's visible.
Okay. So exploring the wonders of the universe. Let me go through this first one. I'm keeping in mind that my audience is students who are young learners, maybe from class 5 to 8. And keeping that in mind, this is a presentation which will be very general. And I'm not taken very specific and scientific detailed concepts. It's overall view. So what is astronomy? It's studying universe and its cosmological aspects and the stars, planets, galaxies. That's what is astronomy. And the key branches of astronomy is observational astronomy, astrophysics, cosmology. And the aim is to explore distant planets, moons. And these are the nearby, you know, moons and this other planets like Mars. We are more interested nowadays. And of course, beyond that, that's the aim to understand. Now, this is just to give an understanding the scale of universe. It's very big, of course, very big. But how big? That's we need to understand. So for that, I have used two different scales. One scale is our own solar system. When we see the sun and surrounding the sun, there are planets and different planets by volume and that in the scale wise, how they look like. So we see the sun is the star and central star, and that's the biggest. And compared to sun, how Jupiter looks, and then after Jupiter is Saturn, and you can see all are coming together after the one after. I think it's visible clearly. So this is one scale, but this is actually very very small compared to if you see the galaxies. So in the right hand side, this is not visible. I know it's not visible. It's not possible to keep it in the same page. So I've got few only. These are the different. This this cursor is. I hope that it's been. As you can see this. That's my cursor. So these are the different galaxies. I'm not going into detail of all the names and these galaxies, but the size-wise, some of the galaxies I've just tried to keep it there, like this. This is the technical. It is known as UCG 10214, and it's known as the tadpole. This is a galaxy, and size is huge. Now, how big it is? Its length of this is 390,000 light year. So that's what I'm saying. The scale is something which is unimaginable even. So these galaxies, if you see that total length is 390,000 light year. That means from one end to another end, if you want to visit, even light will take 390,000 year. This is the length of this galaxy. Of course, it is having a very tall length, a tall tail. Now let's see the next one. That lower left, you see that Milky Way. That's our galaxy, the Milky Way. And if you see this Milky Way is our galaxy, our solar system is actually a dot there. It's not even visible. One single small dot is not even a very prominent dot. It is, somewhere at around 2/3 distance from the center. 2/3 distance from the center, a dot, small dot, which may not be even visible here. That's what the entire solar system, where the sun and all those planets, 8 planets are revolving. And this is what Milky Way. And compared to Milky Way, there's another very nearby, we call it nearby, it's not very nearby, of course, is a galaxy which is Andromeda Galaxy. That's the nearest galaxy of Milky Way is Andromeda Galaxy. And if you see that our own Milky Way, its diameter is 100,000 light year, I mean 1 lakh light year. So that means one end to another end, when light will take 1 lakh year to travel. Okay. And for Andromeda, which is nearby, how much nearby? We say it's the nearest galaxy. And what is the nearest galaxy? It will take 250,000 light year to go there. Okay. And again, this is a very, very large. And what's happening, going to happen, this ultimately, this Milky Way and Andromeda, they are in a collision mode. Collision when made, in another few billion years, they will actually collide each other. And a huge, giant, dark hole will be created. But, it's not going to be near future. It will be billions of years before that actually happens. But it is already in that collision course. That is, Milky Way and Andromeda, they are in that course and moving forward. So black hole is another very, very fascinating thing. Black hole, something which is cannot be observed. And it took many years for the physicists, especially astrophysicists, to pinpoint and locate and make a pinpoint location of black holes. Although theoretically black hole existed, and black hole is something like actually when something, an object which is having a gravity, so huge gravity that even light cannot escape. And it's a very simplistic definition of black hole. So it looks dark, and because it's dark, you cannot take photographs until there are recently the black hole picture was taken. And the black hole picture was taken when actually when the object's huge amount of mass fell on that, then there is a light flare comes out. That was detected, and that's what published in about 2 years back, and that's the first photograph actually taken. And it's called is actually the way it was taken is called Event Horizon Telescope. It's a virtual telescope. It's not a single telescope, which I have shown here in the left hand side. Event Horizon Telescope is actually the worldwide, all the telescopes they are taken, they consider those images, and then they are virtually manipulated to create the image. Now the black holes are interesting because mostly that very huge stars, they will make a black hole finally. In fact, our own Milky Way is having a central black hole, but it's far, we are very far away from that. So this, although black holes actually, whatever object goes there, it never comes out, but we need not be worried about that black hole, which is sitting at the center of the Milky Way even. Next is another fascinating object is exoplanet. Now, what is exoplanet? Is whenever our planets are, like solar system, it is revolving around the solar system. These are solar planet, and the exoplanets are the planets which is revolving around another star, not the sun, which is need not necessarily be even in our galaxy. It can be in another galaxy as well. Even a decade back, the number of exoplanets which were observed were very less, but now we have definite observations of very famous few exoplanets which I have noted here. So you can see this Kepler 22b, then 69c, 452b. These are the exoplanets, and all these exoplanets, if you see, scale-wise, are bigger than the Earth. Okay, and this work is still going on because what happens. Why this study of exoplanets are so interesting, because if any formation of life is possible, it's only possible when these planetary bodies are revolving a sun-like star. It may be a star may be bigger than sun, or maybe the smaller than the sun, and the planet size can be bigger than Earth or smaller than Earth. The importance is the temperature, overall average temperature what it keeps, and the gravitational pull. So the temperature has to be a perfect balance where water in liquid form can exist, and the gravity should be strong enough to have some atmosphere in it. If it is too heavy gravity, then also life form is not possible. If it is too light, it's again not possible. So I'm not going into detail of formation of the what are the necessary factors for formation of the life form, but definitely, and the search for exoplanets are very interesting because of the obvious reason of finding life form there. Another interesting aspects of the astronomy which kept scientists thinking about what's going wrong is the concept of dark matter and dark energy. See, what we see, the observable universe means what we can see, observe in the visible light range. And if you see that total volume of the universe and its total mass, it doesn't match. If you see, the total mass of the universe comes about only 1/3 of what we observe. I mean, actual volume, actual mass should have been 3 times more. So, what is the problem? The problem is there are mass and there are energy which cannot be detected. And that's something very, very fascinating, which is a bit difficult to understand also, that these are called dark matter and dark energy. Even dark energy is actually the most abundant in the universe is dark energy. Dark energy, I mean, is don't go by the name dark. It's dark energy because there's energy which is cannot be observed, cannot be measured with the way we measure the physical quantity. And the dark matter, again, this matter cannot be observed the way we see it, but they exist. Because of their presence, the universe, the entire dynamics of the universe is possible, because the universe is continuously expanding. And the most fascinating fact is that had there not been this dark matter and dark energy, universe would not have expanded. The problem is, if universe stops expanding, it will start contracting. And if universe start contracting, everything will come back to a single point of singularity. That is before Big Bang, what happened? So it started from a speck, one single point. That's the point of singularity. And then there was a Big Bang, this expansion of energy. I'm not going into Big Bang because that itself is the entire presentation. But what I'm trying to tell you, this dark matter or dark energy are very, very important, which keeps this entire dynamics of this expanding universe possible. And dark matter and dark energy are the principal drivers for that. And what is energy and matter conversion? Actually, there is Einstein's famous equation, E is equal to mc square, but no, I'm not going into detail of those again.
Dr. Nath, one of the students have a very interesting questions for you.
Yeah.
Then, with regards to dark matter, dark energy, they are wondering if vacuum is dark matter and dark energy.
No, not at all.
Space.
It's a very interesting question. Someone asked that vacuum is dark matter or energy. No. See, vacuum is absence of matter. Dark matter is not absence of matter. It is the matter, something which cannot be measured by the way we measure, but the way we understand the mass. So dark matter and vacuum are not same, but definitely it's very interesting question. Thank you. Should I go? Or
yes, you can go on.
Yeah. Next, there are very interesting cosmic events. Like all of you know, there's a solar and lunar eclipses. I'm sure that even from space, you keep on engaging students for different aspects of solar eclipse and lunar eclipses. And then there are meteors and then comets. And then there is a very, very interesting supernova. That's the explosion of end of massive stars. So, even supernova can be observed. Those events, are being captured by the very powerful telescopes like Hubble telescopes. Okay. So one of the image at the right corner, you can see there's an explosion of a massive star. And it was actually captured by Hubble telescope. So that's what is astronomical observatories. So there are ground-based ALMA. And that is basically millimeter range observations. It's a millimeter range observation mean which is not visible range observation. What you see a small telescope at the right corner, that's a simple astronomical. That's a simple refracting type telescope, which is in a tube, small telescope, and those are visible range. And bigger than that is also reflecting type telescope. What you see on these planetariums, like different planetariums, if you go, they have bigger telescopes. Those are reflecting type telescope. But what I'm talking about ALMA, these are millimeter range telescopes. So these are radio telescopes. So those telescopes are actually array of uh, receivers, and then those array of receivers, the signal what receives, that is interpreted as signal, and then image is created. A bit difficult than what you see as a visible range telescope, but these telescopes are important to see some other aspects of astronomy. Okay. And VLT, of course, visible light transmission. That way I was talking about that. The telescope, what you know, and what observatories are having, these are all VLTs. Apart from those, these are all ground-based. Apart from those, there are space-based telescope like Hubble I talked about. Then other telescopes like James Webb Space Telescopes. Now, role of technology in astronomy. Of course, astronomy is gaining popularity day by day because of its technological advancement in analyzing its data. So when we analyze the data, as I have mentioned already, it need not necessarily from the visible range data, what you observe, that can be different ranges of data. Like, you can have data which is in X-ray range, or which may be in radio, a signal range. So analyzing those data is very important. And as we are moving ahead with more data analysis, especially artificial intelligence based data analytics. So astronomy is moving even faster at a faster pace. Why I'm saying so, that means to become interested, if you are becoming interested in astronomy, even if you are not astrophysicist, but still with computer science, or maybe engineering in electronics, or maybe in mechatronics, or maybe data analytics, you can still be part of the astronomy, because the technical support system is provided by the data analysis. So it's astronomy is not all about you observe only. Okay, you observe at a visible range only, but that's only a small part of astronomy. But data analytics is very important. So that's how all of you, those who are interested in astronomy, can always be a part of that. Okay. And there are citizen science projects also from for the school going students. And I'm sure that space gives you some opportunity to be part of those citizen science projects, which is based on astronomy. Next is challenges of human space exploration. So space exploration is very fascinating. I'm sure that all of us think about, moving from the Earth to maybe another planet or maybe moon. There are challenges. It's although it's very fascinating, but there are challenges to overcome. And fortunately, the science and technology has given many solutions to that. To overcome the microgravity, to overcome space radiation, to physiological and psychological challenges in isolation of space. So that's how science and technology is going to help more and more. So all of us, those who are interested, can always be part of that, even if we are not maybe astronaut, but still we can develop their products and programs and be part of the entire development cycle, the ecosystem, so that astronomy programs can move faster way. This is something very interesting. I'm sure that many of you have seen this movie Interstellar. And this is, although this is still science fiction, but the way science and technology is moving ahead, I'm sure that we will have enough opportunity in few next 2-3 decades for moving far beyond Earth. Okay, of course, that concepts like the wormholes, so RAB drivers, these are still part of science fiction only. But remember, there are few part of those which is scientifically possible. It's not impossible. For example, there is a concept called time dilation. If you see that movie, those astronomers, some of them went to a distant planet where this time was moving very slow. So when they came back in after a few minutes, by the time 30 years passed. So it seems like science fiction. It is science fiction, but scientifically correct. Okay, because anything which is moving very fast, at the near the speed of sound, for them the time is different than somebody who is static. I'm just giving a simple example, like if you say you are twin brothers. Okay, one of the twin brothers A and B goes on a space flight in a rocket which moves at about 70% of speed of light, and he goes for about say 6 months. And after traveling, remember this space shuttle is traveling at the speed which is about 70% of speed of light, which is, for now, we do not have that technology. Of course, we do not have. That's what I'm saying. Still is the science fiction. But if it is possible that 70% of the speed of the light, the space shuttle is traveling and comes back after 6 months, by that time, on Earth, it will cover almost 30 years. Okay. So that 60 minutes would be comparable to 30 years on Earth, somebody who is, on the Earth. So, which is actually scientifically, it can be proved. You can calculate. But why science fiction? I'm telling because as such, we do not have a space shuttle which can travel at the speed of 70% of the speed of light, which is huge. 70% of near that speed, even we do not have that technology. But if we have, then of course that's possible.
One student has a question, sir.
Yeah.
They're asking that if black holes slow down time, as it is shown in Interstellar, do white holes speed time up?
No, actually, it's not time slows down. It's a different scale. It's basically whenever something is traveling at a speed near the light, that the scale by which you are measuring it becomes different. It's not really slows down. It's apparent. It's basically all the time is a relative. So this comes under this theory of relativity, general theory of relativity and special theory of relativity, which was proposed by Einstein. And again, I'm telling this wormhole concept is still under the preview of science fiction, not really, not a reality, like wormhole from one galaxy to the another galaxy. So you go actually surpass that distance. It will never be possible. Remember that. So whenever I'm saying two galaxies are 1 lakh light year apart, that will remain 1 lakh light year apart. Okay. So don't get confused there. So it's not possible that from the Milky Way galaxy, you go to Andromeda galaxy, which is about 2.5 lakh light year. There will be a wormhole by which you will actually cross it, which is not possible because physics doesn't allow that. What I only said that it is possible, it may be possible near future to build a space shuttle which will be fast enough and which will have this entire support system so that you can take that shuttle to longer duration for time. Okay, that's quite possible in another 2-3 decades. But moving from one galaxy to another galaxy will not be possible because again, there is a physical barrier by which it will restrict your movement to move beyond the speed of light or even near the speed of light. The concept says that if you are trying to travel at the speed of light, then what happens? Your rest mass increases. So it is not that we will never have the ability to move that fast. It's not that ability to move fast. It is a physical barrier by which you will not be able to move faster than light or even the speed of light. It's called rest mass. I'm just giving a simple formula. If you just write it down, it's a m naught is equal to m upon root over 1 minus v square by c square. If you have the time or pen paper, you can just note it down. I have not put those formula because I just wanted to avoid any formula because of your, you are at a class 5 to 8 standard, but somebody had asked the question, so I'm just giving that formula. It's, you can write down m naught is equal to m divided by root over 1 minus v square by c square. Now what happens if v becomes c, c is speed of light, then the denominator becomes 0, and something dividing by denominator 0 becomes undefined. So not possible. So what happens, that time rest must keep increasing. That means the faster you're trying to do, your mass keeps on increasing. Again, this is very, very, strange things to understand. But that exactly will happen if you try to touch the speed of light, which is impossibly large speed. That's why it will never be possible actually to go at that speed. And that's how it will never be possible to go even through that black hole or through that wormhole. All these things will never be possible because physics will simply not allow to do that. Okay.
Yeah.
Yeah.
And we cannot break the laws of physics.
Right. Now, then this career in STEM, I already said that, not all of us need to be astronomers. Not all of us need to work in ISRO. Not all of us need to go to NASA to be in, part of astronomy. In fact, domain expertise will help you. See, if you do whatever you do, maybe you are doing your engineering, or you are doing mathematics, you are doing physics, you are doing chemistry, you are doing biotechnology, you do anything science, of course, you can be part of astronomy because of the huge requirement of data analysis, huge requirement of, space travel for making, the material for the space travel. You have to do material science research because you need those, shields which will protect you from, radiations. You need medicines which will be required, at the space level. So requirements are infinite. So whether it's the engineering, data science, artificial intelligence, biotechnology, environmental science, everywhere the scope do exist. So if you are interested in astronomy, that will be a plus because you will have some domain expertise and you have the technological background, to go for that. Yeah. And this is a continuation of that. Okay, I have already explained that. So this is my conclusion that continuous advancement in space technology drives humanity's exploration. You have to keep doing it because it's not that we are over with our own problems in our own planet, but just thinking of our problems and solution to the planet. Our space exploration should never stop. There are definite reasons for that. And the blend of scientific principles and cutting-edge technology will open new frontiers for the space exploration. And humanity's ultimate quest is to explore, colonize, and understand the universe, which we should keep sustaining and doing it. And as a famous quote by Carl Sagan, that we are a way for the cosmos to know itself. And thank you, I'm through. I stop
Thank
presentation.
you very much, sir. Thank you very much, sir. It is a very enlightening presentation, and I'm sure the students have learned a lot from it, especially the question of that a very simple question that we wouldn't have thought of as an adult. But the difference of, hey, is vacuum a dark matter or dark energy? That by clarifying that it's a different thing entirely, it's a very important thing, and I'm sure the students have benefited much from this presentation.
Right.
Now, the students, while also listening to your presentation, they have gotten some questions, which they are actually, some of them are very eager to ask. So we shall now go to the questions part. And the first question that came to mind, which actually I picked it up directly because we just talked about it, is we know the size of galaxies. We know how large they are. For example, we know the Milky Way is around 100,000 light years across. But the let me just get it. Avani from 6E, the Moria School, they would like to know how we actually can be so sure of this size. How can we be so sure of the galaxy's size?
Okay. It's not that somebody has tried to guess it. It's actually measured, and basically also astronomy gives us an opportunity to see our past. If I say we can actually go to past through astronomy, it may look it seems like impossible. It's not actually. Whenever we're looking at a distant place, say when we are seeing a galaxy which is maybe 100 light years or 1000 light years from us, that means when light reaches us, that time light has traveled actually 1000 years. What does it mean? What we observe is not now, which we're observing is 1000 years older. Okay. That means if we see now, how do you know the universe, age of the universe? Nobody did a radioisotope study for that aging thing. It's basically when you look at these distant places of the galaxy of the entire universe, that time travel, how much time it took, that gives us an idea. So it is basically what we are seeing the past by observing it. And the question was, how do you measure the length? So it's, of course, you can understand this measurement is not by inch tape. It's not a physical measurement. It's a physical laws which will enable us to measure it. So there are different ways and techniques to understand exactly how far that object is, and how much time did it take. And there are other aspects also. It's not like light travels always in straight line. There are gravitational lensing possible. Gravitational lensing means whenever light travels through a very large mass, it bends because of the gravitational pull. So those are also taken care of, and then the distances are measured. Very good question. Yep, it's very technical, highly technical question. Yeah.
Yeah. This has, kids are very curious, so sometimes they think of questions out of the box, as we say.
Right.
So one of the students, you showed the photo of the black hole. So one of the students, Reshna Bhada from Imperial Heritage School, would like to know what's the exact name of the telescope.
Okay, it's a Event Horizon. The telescope name is Event Horizon. Is a Center for Astrophysics in University of Harvard. And remember, this Event Horizon telescope is not a physical telescope. It's a virtual telescope. It's basically, it takes signal from many telescopes around the globe. But the name is Event Horizon. Yeah, that's again right question.
Okay. And I think the word virtual may confuse the students a bit. So could you just expand a bit more on that?
As I said, it's a virtual doesn't mean that there is nothing physical object there. Virtual mean it's not a single telescope. You are not getting data from one telescope. When it's a one telescope, there's a physically telescope exists and you take data from there. But here actually you are taking data from multiple telescopes simultaneously and analyzing the data to create the image. Because when it's a black hole, getting a black hole image is itself is extremely difficult, almost impossible. So it was not so simple. So when the project started, and then they had to collaborate with many telescopes around the globe to analyze the data and create the image. So that's why it's a virtual image. It's not like a camera. You take and shutters and get one image. It's not like that. It's absolutely different. These astronomical images, what image we see, those are not like visible range all the time. It's different. At times it's at the signals are at X-rays, as I said already. Sometimes it's in microwave range. And then those data are analyzed to create the image. That's why I explained the term virtual. Yeah, Event Horizon is a virtual telescope.
Okay. Now, and then Anya Mittal from the Moria School has a question with regards to black holes.
Okay.
If a black hole is found by a star collapsing, how does it turn into a hole?
Okay.
And the second
Okay.
question they have is, it's since it's formed by a star, and we know that stars usually emit light. But why do black holes not emit light? So these two questions I feel are interconnected
Okay.
with each other.
Okay.
So
Okay. Black hole. Although the name suggests black hole, there is no physical hole actually. There is dense matter. Dense. I mean, you can possibly the most dense material you can think of. There's a black hole core. So there is no hole. The black hole, the name black hole, because of the historical reason, the name is given black hole. But because of its extreme gravitational pull, why it becomes extreme gravitational pull? Because whenever the extreme masses they are together, their pull becomes very high. I'm giving an example, simple example. I'm sure the students will understand. Like nucleus is having nucleons like protons and neutrons, and they bind together. Now, what happens? And the nucleus is part of atom. Okay. Now, what happens if you can segregate only nucleus part of atom, and you make like a cube shape or maybe a sphere, small sphere, maybe that table tennis ball shape, made only of nucleus, any nucleus, maybe say uranium nucleus or maybe iron nucleus, not atom, nucleus. If you make them only nucleus, that kind of density it will offer, the earth will not be able to hold it. Even it will make a hole through the earth and it will go, because it will be so heavy. And when it becomes so heavy, its gravitational attraction will also becomes very, very heavy. Okay. And the dark hole, this black hole is something like that. It's extremely heavy. And that's how even when the light goes, it's not able to come out. That's what I said. It's a very simple explanation of black hole. Yeah. And what is the next question? I missed it.
the other question was, why does it not emit light? Which you
Okay.
actually have answered.
Actually,
with,
it is basically what we see, what we observe light is when something gets reflected. Okay. Then only we see this. Now, when nothing is reflecting, everything has been absorbed. So its absorbance is 100%. You see dark. Okay.
okay. So Abhinu Johar asks, do white holes exist?
See, many of these, black hole, of course, exists. White hole and this wormhole, all this, I repeatedly said this is a science fiction concepts.
Students really like their science fiction.
Yeah, very interesting. Many things are not all science fictions are actually physically possible, but still, they are important to keep that interest alive. Yeah.
Okay. Now, Miraya Sharma would like to know, what's the most powerful explosion in the universe?
Oh, most powerful explosion. Maybe there are data required. I do not have that data backup with me, but whenever a massive star that explodes, as I said, supernova, those are the brightest image possible. Any supernova will be the brightest image. Even in naked eye, supernova explosion can be observed, and at times it come, but no, I do not have really the data to say which one is the brightest. I do not have.
Okay. That's still fascinating to know that supernovas can be seen even from
Right.
far away with
Yeah.
our own eyes, when sometimes we can't even see the
Yeah.
stars.
That's the most explosion, huge explosion possible is a supernova. Yeah.
Okay. Miraya also, what it looks like Miraya has a love for black holes, and she would also like to know what happens when matter falls into black holes.
No, nothing happens. Actually, it falls. It goes there, and although this entire energy remains conserved, but it's because of the huge gravity pull, nothing comes out of that. It goes there.
Okay.
It attracts. That's it. Completely, it attracts it. That's it.
So we can just say, like, whatever matters that usually falls into a black hole, we'll never see again.
Yeah, right. But again, the total energy remains conserved and total mass remains conserved. Yeah.
Okay. Then Samyak Jain from Alcon International School once is a bit skeptical about the universe, the expansion of the universe, and would like to know how can we be so sure about the universe expanding.
As I said, the physical law says if universe doesn't expand, it will contract. Because the very reason to get an equilibrium with all the objects and all the the heavenly bodies what we observe is not possible that something which will be static. It will not be possible because gravitational pull is always attractive. Each will attract other. So because of the gravitational attraction, that's a force which is always attractive. That's and it will keep on attracting and it will keep on collapsing. So universe has to expand. It has to expand, and it's not the theory. It is proved that universe is expanding, and it is expanding at the speed which is exactly required to prevent it from contracting. Okay. So you will never be able to achieve to the edge of the universe. That's another physics law. You will never be able to go to the edge of the universe, because the time you are going to you are able to observe the edge of the universe has expanded even further. If universe stops expanding, then for time being it will be in equilibrium. It will stop momentarily, then it will start collapsing. It will contract. And when it starts contracting, it will come to again the same point of singularity.
Okay. So we know that the universe is expanding, and if it doesn't expand, it will contract and collapse into a singularity. Samyak, in addition to his previous question, would also like to know where the universe expands into.
No, where? Okay, you are talking about the space. Okay.
About space.
That's something very genuine question, that the understanding of space and time is not so simple. First of all, that's a Doppler effect. That when universe is expanding, that's proof is Doppler effect. When we see from the distant places. I'm not going into detail of the Doppler effect, but that proves that the universe is expanding. And where universe is going about this space and time domain, again, that's it's not so simple to explain that what is beyond universe. I'm sure that the students is thinking about the space, that the very understanding of space and time and space time interlinked together is extremely difficult, remember. And whenever we talk about this very, very huge scale, that macro scale like universe, and very micro scale like nucleus, atomic nucleus inside, our causal relation doesn't work all the time. Causal relation mean that cause and effect. So say if I make a cause, then I see the effect after that. So that's called causal relation. But whenever you look at those very macro and micro level, then this causal relation doesn't work the way we understand it. So where universe is expanding in the space, thinking about what is space beyond universe, those are the questions cannot be really answered in this certain term, yes and no. For that, actually, you need to have understanding of that level of physics to actually understand that part. Otherwise, it will be like like a storytelling, and storytelling may not do justice to explain those phenomena, which needs relativistic theory, special theory of relativity. Okay, that may not be possible.
Okay. So you mentioned that the universe starts from the Big Bang, and the Big Bang needs a whole other session actually just to talk about it. Miraya also has a question that what is the cosmic microwave background, and what can it tell us about the early universe?
Yeah, that's a very theoretical question. I think all of us know it is a cosmic background. It's basically the signals which captures all the telescopes, especially this radio telescope range. That is the cosmic background itself is proves that early universe, because it's signals which is coming from the distant places. That's basically the background noise, which is basically this microwave noise. So as the universe was created earlier, that time, after that different seconds, different time zone, there are microwave backgrounds are there. Those microwave backgrounds, they have expanded because of the expansion of the universe. And because it's expanding, but that never ended. No, that keeps on, it's still traveling, still traveling. Even whatever farthest distance you go, it's still traveling. So it's coming, it will keep on coming. That's a microwave background, because the microwave was the earliest wave, radio wave, electromagnetic wave, because there's a spectrum. Electromagnetic is there having an entire spectrum. It starts from radio wave, then it goes through microwave, then infrared, then visible light, and microwave, then X-rays and gamma rays. This entire spectrum. So that microwave background is the earliest, universe starting position, and those microwaves are still there. It's coming from the distant places, earliest, the farthest corner of the universe. They are still sending the microwave. That's what called microwave background.
Okay. Then Rashna Bhada, she just would also like a refresher on what is dark matter.
Okay, I think one of my slide was dark matter and dark energy. Basically, these two are together, dark matter and dark energy. There are matter which are not the matter the way we understand matter, and that's called dark matter. And the energy, dark energy, is not the energy the way we understand energy. That's the dark energy. Now, what is the concept of this dark matter and energy? These concepts are required to understand the equilibrium position. Because, as I said, the total mass, what we see, observable mass of the universe, does not justify its expansion. It will not be able to expand with that mass, because it will not have that much of gravitational pull to keep on expanding things. But the dark matter was actually proposed much later, and then it was validated. So dark matter and energy are interchangeable, because matter forms energy. And this entire 75% is most of the things, again, dark energy, not the matter also. So dark matter and energy are part of the universe, very much part of the universe, for the equilibrium of the universe.
Okay. Now, Pranjal from Alcon International School would like to, this is in regards to exoplanets and habitability. So they would like to know if there are any other habitable planets in the universe, and if there is there what's the name of that planet?
No, there is no habitable planet as of now, because there are definite requirements. Some of the requirements I have already specified for a habitable planet, which unfortunately none of these exoplanets are having that parameters fulfilled. All the parameters, not even partial parameters, not even fulfilled. But exoplanets are simply a planet like those planets are orbiting a star. That's called exoplanet. And many planets were discovered in last decade. Now also keep on doing it. And habitability is a difficult choice. Till now, none of these exoplanets shown any characteristics which suggest us this habitability is possible. Even for us, it's challenging to even see our own solar system, because there are moons and planets which seems to be habitable but not. Like, for example, Mars is one of the planets which seems to be habitable, but it's not. And then similarly, one of the moon of Saturn seems to be having a habitable condition, but still now it is not. But such is still on that there is no reason to believe that the Earth is the only planet in the entire universe which is having a kind of a sun-like star and having a perfect distance where water can be at liquid form. We do not know, actually, because the understanding of our life system itself is based on water and then carbon, hydrogen molecules. Okay, that's a living being. We really do not know whether the similar concept, the similar situation exists for the life we understand. It is possible that there may be bacterial form. The bacteria need not need those kind of liquid water to thrive, and the life form is quite possible. But as science doesn't say without any evidence, as of now, there is no evidence. Okay, but that doesn't say there is no possibility. So let's understand this very clearly. There is possibility because, as I say, the universe is so big that we cannot even imagine, because billions of years light takes to travel from one end to another end. And then in that billion years of light travel, there may be millions of solar system like system, and there may be millions of places where the life form is thriving actually, but we do not know. But we should not also say without evidence that there exists. At the same time, we should not also overrule it that it doesn't exist.
Okay. So there's always a possibility that
Of course.
there's life elsewhere.
Yeah.
Picking back of that, Arti Jain has, and if you don't feel comfortable, you don't have to answer this, sir. What is your theory about alien communication?
No, those are no science. Okay, no science. Like all these flying saucers and solar communication by the alien. There is no science behind it. There is no backing of science there. Okay.
Okay.
Because as I said, science say evidence based, and evidence based means it has to be repeatability. Let's understand the methodology of science. Science has to be repeatability. That means if something is happening, then you should be able to do it again. It's not that once only one person saw it, only one place it happened, or once upon a time it happened. No, that is not science. That's not science. It has to be repeatable. It should be provable. You should be able to prove it. Till you prove it, you cannot say that is scientific. So those alien communication, those flying saucers, those everything related to those are unscientific.
Okay. Ridan asks if multiverse theories are true.
See, there are a group of people who considers that multiple universe do exist. Okay, like there are similar what the universe what we understand. There are multiple numbers of those, but those are only theory, and there is no as such genuine proof of that. Okay. And because, as I said, that's whenever it's a very macro level like universe, things are so complicated. Our causal relation doesn't hold the way we understand the causal relation. So even saying that multi-universe exists or do not exist, it's a matter of debate. So scientifically, that's possible, but at the same time, proving it may be extremely difficult.
Okay. And I think this may be a bit of a confusion to the students. So I think it may be best to actually elaborate on this. Could you explain the difference between hypothesis, theories, and laws?
Okay.
Well, I'm sure one student,
Yeah.
when I mentioned, when we talked about...
Hypothesis is something which is not yet proved. For example, I give a hypothesis like in my area, in my locality, in the month of October, this kind of birds are visiting. I said this is a hypothesis. Okay. When I observe, a group of people observe, or I observe, and we repeat the same things again and again, that becomes a theory. Okay. And there is no difference as such between law and theory, because the law is based on the theory. So if we say Newton's law of gravity, that's also theory of gravity. Okay. So, but hypothesis is different. Anybody can do any hypothesis. Remember, making hypothesis is not unscientific, but thinking the hypothesis is right, that's unscientific. Your hypothesis has to be backed up by the scientific methodology and principles to prove it. Then only, because in fact in environmental science there are hypotheses made. For example, somebody will say, okay, the lowlands mean where this water can go and percolate there. The lowlands are essential for thriving a kind of bird, say. That's hypothesis. But over a year, once the observations are made and this claims are actually proved, then it becomes a theory.
Okay.
Hypothesis is a kind of a claim. But of course, it has to be a scientific claim, and there are many things which are unscientific. We don't even consider those hypotheses. Okay.
Okay. So now that we know the difference, Riyashna Bhada would like to know which is we know Milky Way and Andromeda one day is eventually going to collide. So they would like to know which is the bigger galaxy. I guess they have an idea which is the one who's going to win in the collision.
No, there's no win or loss. Remember, there's no win or loss. It's basically when it collides, it's a single form will come. But apparently, the lengthwise, Andromeda is bigger than this Milky Way.
Okay.
But
And
remember,
also,
again, the bigger and smaller is again, it's maybe, its total mass is different because that how the mass density that also matters. So scattering in a different, very distant places, and whereas you are concentrated mass, that's these two are also different games. Okay. So, but apparently this the entire scale, disk to disk, when one end to one end length, Andromeda is bigger than this Milky Way. So it's who is going to win the race is nobody's win or nobody's loss.
okay. Then how do gravitational waves work?
Oh, see, it's an extremely difficult and very technical work. It's a gravitational wave, which is detected only 4 years back. But it was actually proposed a long back. It's basically whenever the light ray travels near the hugely big gravitational pull, it tries to bend. That's called gravitational lensing. And the gravitational wave, understanding and explaining this gravitational wave in this way, as I said, it will be a bit of injustice to explain such a difficult topic. How does gravitational wave work? I don't think I'll be able to do justice here and for that.
Okay.
It has to be need a bit of different, more time and background for the students even to understand that. Yeah.
Okay. Could you just at least tell them like what sort of information we can learn from this event, gravitational waves?
No, it's see, somebody interested about astronomy can actually go for all these events are actually published now. NASA websites and ISRO websites, especially there will be astronomical websites which they have sufficient of information. But my take is a bit different. Don't go by these jargons like this, because that just telling about that may not be sufficient to understand that. Fine. For example, if I start explaining that what is relativity, general theory of relativity, but without having a mathematical background, it will be all the time storytelling format, and you will not make any progress in that. So my suggestion is, rather than doing that, you concentrate on things, you back up your understanding, your learning process with your understanding process. It's not all the time stories. There may be fascinating stories. For example, science fictions are good for motivation, but science fiction stories cannot be taken for your own career path. It cannot be. So learn something which is comprehensible by you, and then as you progress, slowly you will be able to understand more and more. If you have that motivation, if you have interest in that particular subject, you keep doing it. Do not scratch here and there. That is not going to do any progress.
Okay. So Arav Grag has a question which is actually falls right into your wheelhouse, which is, what is the role information and technology plays in space science?
See, information and technology is kind of a tool. Without that, nothing is possible. For example, without doing computer programming and simulation, you cannot do anything. Even for launching a satellite, also you need to have everything. The simulation and then programming, everything is required. So information technology is such a word nowadays that without that, almost everything is impossible, isn't it? When forget about space science, you cannot do railway reservation, you cannot do flight booking without information technology backup. You cannot do this programming, even this online programming, without the backup of information technology. So it's obvious, no? Space science need information technology, isn't it?
Yes. Then, how do spacecrafts lose? Like we keep hearing about Voyager 1, especially Voyager 1 and Voyager 2. They are now in interstellar space. So we always hear about how we may have lost contact with them. So how does this happen?
See, there are two ways communication. One is the Earth-based communication, that communication which goes from these, different observatories and different, sorry, not observatories, different centers. Like ISRO is having their own centers, NASA is having their own centers for deep space communication, and this is called DSS. But apart from that, this most of these spacecraft, they do have their own onboard computers to take decisions. So it's not entirely based on the signals which has been received, and because there is a delay. But at times there has to be, the thruster has to be opened, and there has to be course correction required, depending on this many parameters, because there are sensors all the time. So for that, onboard computers are there to take care of those situations.
Okay. Then um, Manish Jain, this is actually a question I think from within the presentation. They were wanted to clarification on what time dilation was.
Yeah,
I
again,
just got this question. Yeah.
it is I think I've explained already. Time dilation, a kind of story I said. It's very simplistic, as I said, like two twin brothers. Twin brother A and B. B goes on a space shuttle which travels at the speed of 70% of speed of light, and he comes back after 6 months after the space travel. When he comes back, his age, he was that time 30 years. He becomes 30 years 6 months, but his twin brother becomes 60 years when he comes back. So it's 30 years passed in Earth, whereas for him it is like 6 months, which seems to be like science fiction. It seems to be science fiction, but it's actually physics. This is actual physics, because time dilation is based on space dilation. It's a special theory of relativity tells us this way, because the way we perceive time and space is different when you go to that high speed, very high speed, which is extreme speed of light. We cannot imagine actually speed of light. When think about a bullet travels at the speed, very high speed we think of. It is not even a fraction, and measurable fraction compared to the speed of light. Okay, so that's what is time dilation. If very simple way of storytelling format. Time that if you motivate it, is good. It's for motivational purpose. But if you actually want to measure it, if you want to know time dilation, space dilation, space contraction, then you have to have that much of physics background. Okay, it is a very high-end physics which is required to understand. You have to understand these equations, then only you'll be able to actually explain things. Otherwise, again, as I said, it will be always all the time storytelling. Storytelling is one time up to one level is fine, but being a science and technology students, you should not restrict yourself up to storytelling. That can motivate you, but go for further. Yeah.
Okay. Sunita from Jaipur, she asks that we say that we know how the stars grow and evolve over time, but do we have an idea on how galaxies themselves change over time?
See, the galaxies are what? Galaxies are conglomeration of many stars, planets, and these things. So, galaxies are not something different, but whenever we see, the distribution of masses, those masses together, we call it galaxy. So it's not a different thing. No? Galaxy is not another object in the universe. Stars, planets, all together, comets and all other stellar bodies, they make it a galaxy whenever they are in a group. That's what is galaxies.
Okay. Then Nesiga from China, she asks, what are the tools and technologies essential for amateur astronomers? So students who are embarking in their journey. So what should they start working with? What tools should they start using?
First, use your own eye to look at the sky. Of course, Delhi and this polluted cities are not good for looking at the sky. So whenever you are going to outskirt places where the clear sky is visible, have your eyes and mind open to look at the sky first. Read about the sky. Try to learn about those stars and constellations which can be visible at the naked eye. Fine. First. Second, read about it. Third, if possible, have a small, telescope, astronomical telescope, which is very cheap astronomical telescope. This telescopes allows you to, or horizon, increase your horizon. Okay, look at sky. Of course, this telescope should not be, seen daylight, at night only. You try to see, and I think that's good enough to start. And the moment you have all these three, you are an astronomer. You call yourself astronomer, amateur astronomer. Yeah.
Okay. Uh, Chowdhury asks, what are pulsars? And why do they emit pulses of light?
This is something, which we have already covered all these things. When if we keep on talking about this, quester, pulsars, and this, it will keep on never-ending discussion. Let's take questions which are something of STEM related. Yeah.
Okay.
Because we are not going to take like textbook questions. Huh?
The students usually, since some of them, it's like this is the chance they can ask whatever they want.
Yeah.
So
But I
sometimes they
think we have
forget
taken
what questions
those
they want to
questions.
ask, so they
If
just
there is
ask
something like just now, the question was like how to become astronomer. And I want the questions which are coming like from their heart, not just by for asking questions. Yeah.
So one student, they asked like, what would, like, we know that sometimes different planets have different atmospheres, at least the rocky planets. All planets have different atmosphere. So they would like to know how the view would be. Would it be different, or would it be like what we see on Earth?
No, see this rocky planets and the gaseous planets. Of course, these are different, and the differences are how far it is from the star system. So, see, the rocky planets definitely they have the definite core, but gaseous planets need not be entirely gas. They also have a rocky core. For example, Jupiter has a rocky core, but most of the part is gaseous. It's a huge fireball, a huge gas ball, but it has a rocky core. Okay, so as such, that there is not much of difference between this if we talk about the atmosphere. So atmosphere, if it is a gas, entirely gas, then say there is no fine line of difference between gas and the mantle, which is a rock. Okay, whereas the rocky planets, like for example, Earth is a rocky planet. So there is a fine difference. There are a clear definition of what is atmosphere and what is the rock. Okay.
Yes.
Yeah.
Okay. Then a future astronaut is asking, what do astronauts have to do to prepare for zero gravity environments?
Oh, you have already reached that to that space.
Yes.
You don't have to be worried. So if you are at that level, you will be trained enough, for zero gravity. There are tools and techniques where the agencies which will send you, they will train you. So you don't have to be worried about too much. But I'm sure that you need to be worried about now that you need to study first. You need to be at that level before you are actually being sent to space. Okay, zero gravity will come after that. First, now there's within this Earth gravity, you first be motivated and widen your scope of understanding, learning. Of course, you have to learn the subjects as per the syllabus, but having always curiosity to know more, because that always is a big plus. Aiming for something, dreaming something and achieving it. Of course, if you dream, you can always achieve it, but only dreaming but not taking action is no good. Okay, so don't have to be worried about how to prepare yourself for the zero gravity. That will be taken care of by the system. But what you can definitely do, you learn more now. That's the best part now. Learn.
Okay. Recently, oh wait, sorry. The International Space Station is like one of the modern wonders of the world. And students, since they are not used to it, they have only heard of it. They are interested to know if it's if it's a possible to see actually from the ground, and how do you track it, basic? How do you
No,
track
no.
it to find it?
You can't see it from the ground, International Space Station. You cannot see it. It's not possible. But astronomers are actually, keep on moving there, going there. I think you are sure about know about Sunita Uliam. She recently went there. She is there, and astronomers are there regularly, all the time. In fact, there are astronomers there, and they do a lot of research there. Because on biotechnology, on physics, and on material science, they do observations. There are labs also, and that's very important for us. Those research are very important for us, which sheds extra light, because whatever experiments what we do here and the experiments which is been done there are not same. So it's very important for us.
Okay. Then we have several space telescopes now. Before, I'm sure there was once a time when we had none, but now we have several space telescopes, and they have changed our understanding of the universe. So how have these telescopes like Hubble, James Webb, it changed the way we view the universe?
Of course, there's a plus, big plus. The telescope, which is beyond Earth and taking images, that's devoid of all the other interferences from on the Earth. So because it is up on the atmosphere, so it takes clear images and no distraction. So it will be able to take better images. And because of that, highly technologically advanced telescopes. So of course, the kind of image which has shown us, that's nowhere possible from the Earth. You would not have been able to take those images. So definitely, it's a big plus, and it opens, many aspects of the universe which we never knew. So the kind of images Hubble has given us of, that has opened up many other research areas, and that data analysis is very much important for many astrophysicists. They do use those data. There are many students, research scholars, they work on the data received by those telescopes.
Okay. So Ridan is asking, like, what's the next big thing astronomy has to look forward to? From what I remember, for the longest time, it was we know by theory black holes are real. Then within the last decade, we actually got to see one, and that was a big deal. Seeing the black hole after having theories for decades. So they would like to know what's the next big thing for astronomy to look forward to.
No, I think it cannot be pinpointed like this is this because we do not really know. So maybe search for extraterrestrial life, it will keep continuing. And of course, the space travel is space travel need not necessarily going to far away places, but space travel is going to be very common in another maybe decade. Then maybe resource utilization from the moon and the Mars, which is possible. Utilization of those resources, maybe making a center to for there's a launching pad, making launching pad at moon or at Mars. They may have their own definite advantages. So those are the things which is very common. And apart from that, different space mission keep on doing it. NASA will keep on doing it. European space agencies, ISRO, they will keep doing their own space missions for exploring the universe more and more. And that learning is never ending.
Okay. Yeah, learning never ends, especially when it comes to space. Who's this? One Sharnaya asked, why do galaxies? This is again referring to your slides. She saw many types of galaxies on the slide. So she wants to know, why do they have such difference in shapes, sizes, lengths?
Okay, this is mostly is a random, because it's a what is the galaxy is nobody forms those galaxies this way. It's basically the concentration of masses. Okay, it's concentration of masses, and when you see there are concentration of masses, we say, okay, this is the galaxy. That the name is given by us. Okay, and then there are gap, and then again you see many masses, and then we shape. So the shape, what you see, the shape is only kind of a concentration of masses are there. That's it. And then after that there are gap, and then again see some concentration of mass. So whatever is the size and shape, it comes like that.
Okay. Then this is not related to galaxies, but it's again related to stars, where they we can tell a size, we can again guess the size of a star. So how can we guess like the biggest stars in the universe? What is the criteria for a biggest star in the universe? And is what's the name of the current one holding that title?
Oh my God! This biggest star, I don't know. This biggest star, stars are in all the galaxies. I mean, the galaxies are full of
Yeah,
stars only. So I do not know whether there is any such nomenclature of biggest star kind of thing. At least not in my knowledge. There must be, but I'm not aware which one is called biggest star in the entire universe.
no. So they, but that's also they we did the classification for that is also very vague, classifying a biggest star.
Yeah, there must be some stars which is classified as big star, but I do not have that information.
Okay. So going back to living on other planets, one of the many steps in the future being living in a Mars or moon. What sort of technology you think is important for that leap to happen? Like the leap to the moon, now leap to Mars, living on the moon and all. What sort of technology you think needs to come about for such things to happen?
See, this colonizing the moon or the Mars is, many people's dream, and a group section of people do believe that it's very important to colonize Mars and these things. But there are differences in opinions in among scientists and policymakers whether uh, how many people are going to get benefit out of that colonizing it. And that's what I precisely said, that maybe the utilization of the resources would be the better interest for the people, rather than thinking of the full colonization as of now. um, that's something which is political influence, and then and that kind of funding that will determine the future course of action. I don't have much of an opinion on that. But colonization, if it's not impossible, as I said, scientifically possible, but the cost of colonization would be huge. Cost of
Okay.
colonization in Mars or in moon is going to be huge, and if the outcome is not huge, then the justifying that huge cost would be also a very difficult proposition. So it has to be taken in that way. It's, although it seems very nice, and see movies on those, people are living in Mars and regularly, getting things are getting transferred from the Mars and these things. But feasibility is and affordability, feasibility, whether that will be cost effective, that need to be worked on. And it's not only scientific; it's also political things, involved in that. Scientifically, yes, possible.
Okay. So unfortunately, it looks like it is time for our time together has ended. So thanks a lot, Dr. Nath, for have your presence and for enlightening our students today.
Thank you.
Look forward to having you again soon.
Thank you.
Thank you very much. And thank you for everyone for your attendance. We hope you had fun today.
Should I leave now?
Just 1 second, sir. Let me just. Okay.